Greetings, everyone. My name is Dr. George Nield. I'm currently serving as the chairman of the Global Spaceport Alliance. Today, I'd like to welcome you to a special briefing on revolutionizing access to space. The video that we just saw featured the Aurora spaceplane, which has been developed by Dawn Aerospace and which is currently undergoing flight testing in New Zealand. That spaceplane has the potential to offer access to space from a runway on an almost daily basis at a price point that is expected to be about an order of magnitude less than existing suborbital systems. A few hours ago, Dawn Aerospace issued a press release containing a major announcement about their plans, and we are excited to have Stefan Powell, CEO of Dawn Aerospace, with us today to talk about that announcement and their vision for the future. We'll also have plenty of time for questions, but before I turn it over to Stefan, I want to again thank our platinum sponsors, RSNH and Merrick, our gold sponsors, BRPH, Parsons, and ITA, and our silver sponsors, HDR and MITRE. They have contributed significantly to GSA's recent successes as an organization, and we really appreciate their support and encouragement. This time, I'd like to introduce Stefan Powell, CEO of Dawn Aerospace. Stefan has a bachelor's degree in aerospace from Delft University of Technology and a master's degree in space systems engineering, also from Delft. He served as a propulsion intern for Rocket Lab and later worked as a propulsion engineer at Hyperion Technologies. In 2017, he was one of the original co-founders of Dawn Aerospace, where he currently serves as both CEO and CTO. Stefan, thanks so much for being here today, and thanks to Dawn Aerospace for agreeing to become a member of the Global Spaceport Alliance.
Yeah, thanks, George. Thanks for the kind intro. And yeah, we're very happy to be joining the Spaceport Alliance as well. This is a fantastic community, and I'm very glad to be able to talk to you all here today. So let's get this presentation going. Yeah, so obviously I'm here to talk to you all here today about our the press release that's just gone out. It's our offering that we're actually selling the vehicle now, a vehicle capable of reaching space at 100 kilometers altitude in a suborbital flight. And I'm very excited to be presenting this to the Global Spaceport Alliance, especially because ultimately I hope that you all are one of the key beneficiaries of vehicles like this. You know, horizontal takeoff and landing. It really makes suborbital access to space a lot more accessible. This is a vehicle that we can fly from many new spaceports around the world. But now, before I get into the detail of this vehicle, I just want to give you a little bit of quick background on Dawn. So we're founded in 2018. We're about 120 people now. Our headquarters is in Christchurch, New Zealand, but we have major offices in the Netherlands and an office in the USA and France as well. So our core mission is scalable and sustainable space transportation. And while we started building Aurora in 2018, it's not by a long shot the first product that we've actually offered to market. The first problem in scalable and sustainable space transportation, in our view, was actually in-space propulsion. And this is a much simpler problem to solve. The problem that we saw there in responsive, scalable space transportation was actually hydrazine, a chemical propulsion, highly toxic, very effective, but ultimately just needed replacing at some point. So we replaced this with nitrous oxide and propylene. There's a picture of one of them up here on the right. You know, since getting the first one of those in space in 2020, you know, we now have over 100 thrusters in space on 26 satellites. This business line is well developed. We'll be producing about 50 propulsion systems for satellites this year. So the majority of these go to low Earth orbit, but we also work on lunar missions. The propulsion system in the top right-hand corner is actually already in deep space now. That's well out beyond the moon. So we have a very proud history and track record here of delivering cutting edge technology to customers all over the world, actually. But, obviously I'm not here to sell you a propulsion system. I'm here because I want to tell you about the other part of our mission, which is all about access to space. Now, everyone here is well aware of the value to space, and there's an incredible amount of infrastructure out there, spaceport infrastructure, to support that mission of getting things to space and bringing this value of space back down to Earth. Now, with so many spaceports out there, why is it that actually the majority of spaceflight happens from only a small handful of these spaceports? Why are the rest of them apparently so underutilized? Well, we believe the fundamental issue here is that those who develop spaceflight capability, they tend to hold on to it for themselves. They don't want to sell you the capability; they'll sell you the service to get to space. If we look at a launch provider like SpaceX, they'll happily sell you a ride, and they do so, many would say, at a very reasonable price. But they won't sell you the capability. They won't sell you the rocket, the ground support, and everything that you need to operate the service yourself so that you can bring it to wherever you would actually prefer to have it. Now, there's many good reasons why they don't do this, good business as well as technical reasons why that just doesn't really particularly make sense. So this is not a dig at SpaceX, but ultimately the fact that the fundamental architecture of the industry doesn't allow for this capability to be exported and owned limits the scalability of it. So there are many out there who would love to have this capability and be willing to pay for it, but they simply can't get their hands on it. It's not out there. It's not for sale. So when we look at highly scalable aerospace industries, I believe there is a fantastic example to look at, and that is aviation, the airline model. So here is a picture of one of KLM's very early airlines. Now, I'm also a Dutch citizen. I studied in the Netherlands, so maybe I have a soft spot with KLM. But KLM is the longest surviving airline in the world. Still with its original name. It's over 100 years old now. They've got nearly 200 aircraft in service, but worldwide there's about 30,000 commercial aircraft. It takes a little over an hour for commercial aircraft to do as many takeoff and as many flights as spaceflight has ever done. Imagine that. It's an industry that in 1 hour does as much as another industry has ever done, at least in terms of number of flights. So clearly, the airline model presents us with a far more scalable model for transportation, and one that we would really like to draw on. And so that's really where we draw a lot of our inspiration for how we want to bring spaceflight to the world, and how we built Aurora. Ultimately, this is an aircraft with the performance of a rocket, not a rocket with wings. That is to say, reliability, reusability, and ultimately scalability are not afterthoughts. They're things that are baked in from day one to enable this airline model. When you really boil down to what does that mean in terms of technical decisions, it means we have highly redundant systems, safe failure modes, just like you have on an aircraft. This vehicle is pilotable. It has lots of autonomous features on board. The vehicle can essentially fly itself, but especially for certification reasons, it's much, much simpler and more scalable to be pilotable. You can fly very frequently. We've demonstrated 6-hour turnaround times. 4-hour turnaround times is absolutely achievable. And we use common infrastructure. We fly out of existing airports. We don't have to build a new dedicated launch pad with dedicated facilities every time we want to launch from a new spot. So the performance of the rocket part is obviously a very important aspect. We can't just be another aircraft. So, of course, Aurora has to have out-of-this-world performance. Eventually, Aurora will hold 3 records for aircraft. It will be the highest flying aircraft ever to take off from a runway, the fastest flying and the highest climb rate aircraft ever to take off from a runway. So now with a 4-hour turnaround time, that would make it the first aircraft ever, the first vehicle of any kind actually, to fly above the Kármán line twice in one day. So it'll have a modest payload capacity, about 10 kilograms max, 6 kilograms to 100 kilometers altitude. That will give you just on 3 minutes of microgravity time. Now, this is enough to perform many interesting experiments, such as crystallization of, say, semiconductors or life sciences experiments, new superalloys. And with this sort of performance, we also anticipate many applications in the defense sector as well, such as target presentation, intelligence, surveillance, and reconnaissance type missions. Yeah. But on this sheet, on this particular slide, of all of these particular metrics, the one that I hold that I'm actually the most proud of is the turnaround time. That's the bit that is so important and so driving in the underlying economics of a vehicle like this. Ultimately, aircraft make money in the air, not on the ground. So that's incredibly important that that number is very, very low. And I'll talk a little bit more about the economics later. But let's have a quick look at what an actual flight looks like. So as you saw in the video, this vehicle is horizontal takeoff and landing. That flight was to 80,000 feet. This is an image of what a flight to over 330,000 feet, 100 kilometers altitude looks like. Once it takes off horizontally, it flies very much like a suborbital rocket in that it is pretty much straight up. Once you're out of the atmosphere, you fly up like this. And once you come back down, there's no atmosphere until you get to about here. You start re-entering, you do a pull-up maneuver, you turn around, and then you come back home. So, that suborbital portion here is about 3 minutes, and then the glide back home can be about another 25 minutes. So your entire flight time is around the 30-minute mark. So talk to you a little bit about the operations, and fortunately, Aurora has given us a fantastic view of the airport that we actually operate out of here. So this is a picture of where we've flown out of before in Glen Tanner. It's a very modest facility. It's a 1,000-meter chip seal runway. Yeah, Aurora can be operated with a crew of 8. We can do full training for that crew as well. Supporting equipment is also very simple. You can see it on the ground here. It's a few trailers. There's a hangar there. All of the ground support equipment we can supply as well. So that's a mission control center, communications ground segment, and propellant loading equipment is all part of a package we can deliver to customers. The vehicle itself, it's not a large vehicle. It's about 450 kilograms loaded and 124 unloaded. That's just on 1,000 pounds. At 124 kilograms, 270 pounds, 4 people can lift the entire vehicle. It's about 5 meters long, 2.4 meter wingspan. The engine is a liquid bipropellant using the electric pump cycle. The engine is throttleable, it's in-flight restartable. In many ways, it acts and operates like a jet engine, has, say, failure modes. You can have complete failure of the engine and you still get the aircraft on the ground. Propellants, 90% hydrogen peroxide and kerosene D60, not RP1. We don't need fancy kerosene. This stuff is cheap as chips. And the communications, direct and dual redundant S-band links and UHF as well. Aerodynamic control through redundant elevons and a split rudder aero brake as well, which helps with controlling energy on descent. And beyond the atmosphere, we have reaction control thrusters, hydrogen peroxide monoprop thrusters. This is essentially the same method that the X-15 used for controlling flight outside the atmosphere. But now the whole point of these decisions, the whole point of this philosophy is ultimately to drive a revenue generation model, like how. And so I wanted to at least put a few words to that. How we anticipate generating revenue. Based on the market feedback that we've had, we believe a per flight price of around the $100,000 mark is absolutely tenable. In fact, in many cases, I think the price could be much, much higher than that, especially when you're talking about custom trajectories, solving really difficult niche problems for which there is no real good solution. A ticket price of $100,000 is very tenable. Based on the testing to date, doing turnaround times of 6 hours in an R&D context in the range of whether we believe we can fly. We believe a flight cadence of about 100 flights per annum is absolutely achievable. In many cases, higher than that is also possible. And with a design life of 1,000 flights, that means your total lifetime revenue is in the order of $100 million per vehicle. Now while I won't speak specifically to pricing, because that is something that we're still really discovering how exactly we're going to price this vehicle. I will say, it will be a fraction of that $100 million USD figure. But the actual price that we present to customers will be something that we tailor to each customer's needs. It's also very dependent on what they need in terms of support to actually operate the vehicle. So anyone who is seriously interested, we highly encourage them to come to us, and we can put together that package of what's actually required. So what have we actually achieved so far? You've seen that video at the start. To date, we've done over 50 flights. On that 57th flight, we flew to 82,500 feet. That's over 25 kilometers altitude. That's about as high as an SR-71 Blackbird flew. That's above 98% of the atmosphere. We also flew supersonic in an 85-degree climb, and we climbed faster from ground to above 20 kilometers, faster than any aircraft ever had. The previous record holder for that was a completely stripped out F-15 that did that in 1975. So it was an almost 50-year-old record at the time that we broke it. So indeed, we're already exceeding the performance of most aircraft, and in some ways, every aircraft. We're now undergoing an upgrade program to increase the propellant mass, the thrust, and include a reaction control system for the next vehicle. But the next vehicle will have exactly the same plan form, exactly the same out of mold line of this original aircraft. That the point of this original aircraft was to break the sound barrier and show that we understood what that took to demonstrate vehicle stability through that regime. Now we have real confidence in that design, and we can build the full performance version. So that upgrade program will take about another 2 years from now. We're scheduled to complete that in 2027, with first delivery to customers happening that year. So we're really confident in the performance of the vehicle. We're confident that what I've presented here today, these projected capabilities to be able to reach 100 kilometers altitude multiple times a day is indeed achievable. We have the skills, we have the experience, we believe we have the track record to pull this off. And thus now is the right time to really come to the community and engage and say, hey, this is really coming. We really believe in this. We see ourselves as the original equipment manufacturer. We don't see ourselves as the operator, because we really believe in this airline model. So I'm coming to you today saying, we want to find the operators for this vehicle. And we believe the spaceports have an absolutely key role in helping us roll out this model to the world. So if you have a runway, you have access, you have airspace to over 100 kilometers altitude, and you believe that you have a need for space access, then please come talk to us. Myself, Catherine, Kaki, Catherine based in New Zealand, Kaki leads our US sales team. Please come to us with your questions. Please come to us with your inquiries. We're expecting the first deliveries in 2027, so that gives us some time to consider who is going to be the first operators of this vehicle. But yeah, we'd love to talk to you all. Thanks very much. Happy to take any questions.
Thank you, Stefan. That was an excellent presentation. For those who have questions, please type those into the chat box and we'll get to as many as we can. But before we start, if I could, I'd like to just provide some additional context for why I think this development is so important for spaceports and other members of GSA. As Stefan pointed out, that there's a lot of current and proposed spaceports out there. There's currently 14 FAA licensed spaceports in the United States and another dozen who have expressed publicly their desire to eventually turn in an application. Bryce Tech has put out their map, which Stefan showed, that shows almost 100 current or proposed spaceports in the world. 38 of those are members of the Global Spaceport Alliance, but very few of them are regularly conducting launches today. And Stefan talked a little bit about some of the reasons for that. In some cases, it's because they don't have the extensive and usually rather expensive infrastructure needed to support most of the vertical launch vehicles that are flying today. In other cases, it's because they're near densely populated areas, and it just isn't practical to safely launch and land large vertical rockets in such a location. But a vehicle like the one Dawn Aerospace has developed changes all of that. With a small, reusable system that can operate from a standard runway, there's no reason why any spaceport with a runway couldn't provide regular access to space. And as all of you have heard me say many times, spaceports are not just places from which to launch rockets. They can also be focal points, technology hubs with aerospace manufacturing and testing, research and development, education and training, workforce development, and in the not too distant future, point-to-point transportation through space. And all of those activities can contribute to the global space economy. So I think what you're announcing here today is really going to be a game changer. Stefan, any additional comments on that perspective?
Oh yeah, absolutely. I mean, this is all about making this more accessible for many others. I see one question out there around the certification and licensing, and that's another aspect that we really want to make this more accessible to others. Now, we in New Zealand, we're able to license this as an aircraft with a high altitude license. That's not something that we can directly export to the world because it is, every jurisdiction will have their own certification method. But we draw on many international standards for how we build up our certification, and we're now working with other major regulators around the world. For example, talking to the FAA as well, for how we're going to certify this vehicle there, so that we can then have a certification model that we bring to the many, the 14 licensed spaceports in the United States. Likely there will always be some local aspect to certification, but that is something that is much more scalable. And the certification that we go after is typically one of a single certification that allows us to then fly many times under that certification without a certification per launch. So once again, going for a much more scalable, accessible model, and that's something that we, as the original equipment manufacturer, can help the operator with, because we have obviously experience with the vehicle, but with certification itself. So yeah, we're doing everything that we can, be it the technology in the vehicle itself, the infrastructure that we require, and the regulation that we require. Those are really the three pillars that we have to work on to make space truly accessible for those who want to operate.
I know you're already talking to potential experimenters and payload developers. Can you tell us a little bit about the current payload customers that you're engaged with?
Yeah. So there's four publicly announced payload customers that we're working with. Three universities. That's Cal Poly, Cal Poly, Arizona State, and Johns Hopkins. All have three fantastic payloads. And then one commercial company, Scout Space. So they actually all came to us very early on, wanting to fly with us even before we had done anything close to actually reaching space. And that really, that was kind of part of the penny dropping for us of, oh, hey, actually, we had originally built this vehicle as a technology demonstrator for a two-stage to orbit system, a better way to get to orbit. And we started realizing, hey, actually, there is commercial demand out there, even at this much lower performance level than we had anticipated, not even suborbital space. This is really just high altitude flight. There's commercial demand there. And then we started digging deeper on that, and we see actually there's real commercial demand in suborbital flight, even with this smaller vehicle size. So that's also part of the reason why this vehicle is so small. It was originally envisioned as a technology demonstrator. But yeah, it's because there has been this technology pull. This has not been us pushing the vehicle. It's been customers wanting to get their hands on it. That's led us to actually offer it to market.
Very good. We have a commenter congratulating you, but also noting that selling the vehicle can be a risk, and observing that one reason why SpaceX may not sell its engines is because they don't want to see them grounded if a customer user has a failure. Any thoughts on that concern?
Yes, absolutely. That's a risk. I mean, this is part of the risk is being on the bleeding edge of this sort of thing. Luckily, there is quite a lot of history in the airline industry. Aviation, as I mentioned, has been around over 100 years, so they are well informed on how to deal with these sorts of issues. Aircraft do crash. The FAA and other regulatory agencies have a way of investigating those crashes that's pretty robust, figuring out whether this was operator error or whether this was a design flaw in the aircraft. We've seen that play out over the years. Most famously recently with the Boeing 737neo, where they found, yes, okay, that these crashes were actually because of the operator, and then the aircraft is rightfully grounded. But there are also many other issues where it's very quickly deduced, no, this was indeed operator error or pilot error, whatever, and everybody else is allowed to keep operating. So in that sense, like, once again, there are models, like the airline model provides us with a very robust, tried and true way of dealing with these sorts of issues. We might be the first ones to be bringing space to the airline industry, but the airline industry has dealt with the same issues that we're going to deal with for 100 years now. So that's exactly why we want to be an aircraft with the performance of a rocket, not a rocket with wings, because we can draw on that airline industry experience.
Very good. Had a question about what is the next altitude objective during the flight testing and the timeline to try to achieve that?
Yeah, so we intend to bring this upgraded vehicle to first flight in about 18 months, and then slightly before that actually, and then the actual flight test program is about 6 to 9 months of flying after that. Now, the actual altitude milestones happen very, very quickly. We on this first generation aircraft, we spent years actually flying only up to about 9,000 feet. And then we went from 9,000 feet to 80,000 feet in like 6 flights. That was a few months. So we anticipate flying this first vehicle for the first time. You really just get it off the ground. You prove the avionics, you prove the airframe, everything. That's not really about performance. You prove that out in very safe ways. We'll be doing those first flights like I say, in about 18 months. And then you very quickly progress from those flights to flying to the edge of the atmosphere and then actually flying way beyond the atmosphere. There's kind of a zone in the middle that's very, very hard to fly to, where you don't get enough time to reorient your vehicle for re-entry. So we'll very quickly go from 80,000 feet to more like 200,000 feet in just a few flights. And then we'll progress from 200,000 feet up to 300,000 feet in another few flights. So the altitude progression versus time will be very, very quick. It might, it'll take us some time to get to that first flight of the upgraded vehicle, though.
Can you share anything about your plans for scaling vehicle manufacturing?
Yeah, so like that's one of the keys for, one of the reasons that we want to really properly approach the market now is to assess the actual scale of demand out there. We anticipate we could get to delivering about 5 vehicles per annum within the next sort of three or 4 years is absolutely achievable. Like I said, this is not an incredibly large vehicle. Most of the production is in-house, so we have good control over that. We have a lot of experience in scaling manufacturing as well with in our satellite propulsion division. We already produce about 200 thrusters a year. These are complex but relatively small products that we have a good confidence in delivering. But if market demand proves to be significantly more than 5 vehicles a year, we could absolutely scale this to a significantly larger production line within the next 5 years.
Okay. Had a question on, does the engine have the same design life as the vehicle, or is there an engine refurb replacement cycle, and what is the engine cycle?
Yeah, so the engine cycle is liquid pump-fed bipropellant, so that's like an electric cycle. So there's electric motors that drive centrifugal pumps, and the oxidizer goes through a regenerative cooling cycle, and then through a catalyst pack. Catalyst pack decomposes the peroxide to oxygen and steam, and then you inject kerosene on top of that, and that auto ignites because it's oxygen at 800 degrees Celsius. That'll auto ignite with the kerosene, and then out it goes. Very simple cycle, no igniters, no igniter fluids. That's fantastic. Nothing to maintain in that respect. Yes, there is absolutely a maintenance cycle on the engine. Catalyst packs do need to be replaced after about 5 to 10 flights, depending on some conditions. Pump seals need to be replaced every now and then. The liner in the engine is also a life item, but all of these are just part of a maintenance schedule, and that's built into the cost structure of the vehicle. None of these components are particularly expensive. The engine can be taken out of the aircraft, maintained, serviced, and put back in the aircraft in less than a day. So you're looking at downtime for maintenance and whatnot is less than 15% of the vehicle life.
Very good. Question again. Congratulations on the aircraft. Great presentation. How about considerations regarding operations in busy airspace, such as the East Coast of Florida? Nearly straight up and down profile seems challenging to integrate. Thoughts on that?
Yeah, so absolutely. Of course, integrating a vehicle like this in less busy airspace is always going to be easier. How exactly we do that in different jurisdictions is still something that we're going to discover. I can speak to specifically how we do this in New Zealand. Fortunately, our airspace is not nearly as busy as it is in Florida, so that makes it easier. But we do literally integrate with other airspace users. We do not fly in exclusive airspace in New Zealand today. Those flights that we did out of Glentana, if you look at Glentana, that's right on the flight route between Auckland and Queenstown, which is a relatively busy for New Zealand at least, commercial route. There's dozens of flights a day passing overhead. On several of those flights where we flew through 40,000 feet, commercial aviation altitude, we flew through that at close to supersonic speeds, and we were able to do that coordinating with air traffic control, waiting for flights to go overhead. In one case, we were actually sitting on the end of the runway, and we were waiting for a Jetstar flight to pass overhead. We waited, some minutes for it to go past, and then we got clearance to actually fly. We flew in behind it, flew up through 40,000 feet at an ascent rate of over 300 knots. Is a very interesting radio call, actually, where we call, our aircraft ascending to flight level 800 vertically. This was actually a call that we had to work out with New Zealand air traffic control of how to communicate our flight profile, because it is strange. And we've had some other aviators call back saying, are you sure you're ascending to flight level 800, not 080? And we call back, no, ascending to flight level 800. So this is something we're going, we are on the bleeding edge here to some extent. This is something we're going to have to tease out and understand how we integrate, especially in these busier areas, are going to be more challenging. But there is actually at least something to push on here. There is, we're setting precedent in New Zealand. We're figuring out how this works in a much more pliable jurisdiction, and then we can start to bring this to new jurisdictions and show how, like, we have done this in New Zealand. Maybe we don't want to do that in Florida as the starting point in the US, but we can do it elsewhere as the starting point, and then we can start to push the envelope in the US and grow trust with the FAA and bring this to ever busier places. And every time we do, this vehicle becomes more accessible, more useful to the world, and we can service more people.
Okay, and one final question. This vehicle is obviously designed to get to 100 kilometers and pretty much straight up and straight down. But have you thought about in the future having a version that could be point-to-point capable?
Yes, absolutely, it's possible. So it's not part of the existing technology stack in the sense that the avionics are not yet designed to do that. But if there's someone who seriously wants to do that, the vehicle itself, with an avionics upgrade, absolutely could do it. And that's not, that's obviously not some crazy new technology. You need to think about the communications architecture of how you do. Right now we have the communications ground segment is in one location, so you'd want to be sure that you have good comms when you're several hundred kilometers away. So you'll want to have a separate dedicated ground communication system there, or a more location agnostic communication system, say via satellite. But this is essentially a communications problem. It's not a vehicle problem. But yeah, if there's real value in doing that, we would love to talk to whoever sees that value and wants to make it happen.
Outstanding. Well, thank you very much. That was an outstanding presentation and great discussion. Good questions. Thank you, Stefan, for that, and the entire Dawn team. Thanks again to our sponsors and to all those who called in today to hear the presentation. We look forward to seeing everyone again soon.